Okay, so this video is about section 2.2 from the textbook, and we're going to introduce the limit of a function. So here I have a graph of the line y equals 3x minus 1, and what we're going to look at is we're going to ask ourselves, as the x values approach 1, what are the y values of the function approaching? Okay, so as I get closer and closer to 1 on either side, the question is, well, what are my y values approaching? We can see that this is what the graph is doing, and we can also see that the y values are actually approaching 2. Okay, so this is the idea, is to ask, as the values of x approach 1, what do the values of f of x approach? And we can see that they're approaching the value 2. Now, the way that we express this in mathematical notation is we say that the limit as x approaches 1 of f of x is equal to 2. Okay. Now, another thing I want to point out is I can approach 1 from the right, or I can approach 1 from the left. And it's possible that I get a different value for my limit. And so what we do is, if we're approaching x from the right, we call this the right-hand limit. Okay, and we use this notation. So the limit as x approaches 1 from the right of 3x minus 1 is 2. Okay, and this is the notation right here. And then naturally, if you're approaching 1 from the left, we call this the left-hand limit. And the notation that we use is the following. So there's a little superscript of a negative there, minus sign. We write our function, and it happens to be the same. Okay, so in this case, if the left and the right limits exist and they're equal to each other, then we say that the limit, like the limit, exists. And sometimes this is called the two-sided limit or the limit. So a key theorem that we have is that the two-sided limit of a function f as x approaches a is equal to L if and only if the right-hand limit is equal to L and the left-hand limit is also equal to L. So in other words, a limit only exists when the left and the right limits are equal. Okay, and if these limits are equal and they exist, then our limit also exists. So these things go together. Next, I'd like to just do another example of this skill. This skill is computing limits from a graph. So here I have a graph of a function f. And you can see this graph does a lot more, has interesting behavior. It's broken into a bunch of pieces. So the limit as x approaches 2, well, these are the x values. As x approaches 2, I look at what my function is doing. It's going down this way. And it appears that the y values are going down and they're approaching 1. Okay, and notice how the left and the right limit are both equal to 1 also. But notice that f of 2, so if I were to calculate f of 2, then f of 2 is actually 2. So it's not the same as the limit, and that's something that's interesting. So f of 2 is 2. It's right here. Okay, so my limit doesn't have to equal the function's value at that particular x. The next limit I want to compute is the limit of f of x as x approaches 4, but only from the left. So I'm going to go back up to my graph, and I find 4, and this is the left side of 4. Okay, so these are values of x that are smaller than 4, and I can see that the graph is here. So the outputs, okay, the y values are approaching 3. And now I'm going to look on the other side, okay, the limit as x approaches 4 from the right. So going back to my graph, if I approach 4 from the right, I find that my graph over that interval, the graph is over here, and the y values seem to be approaching 5. Okay, so let's fill that in. Okay, so the interesting thing is that the limits are not the same on the left and the right, and we know that what that means is that the limit as x approaches 4 does not exist. Because remember, the previous theorem told us that in order for a limit to exist, the right and the left limits have to be equal. And here they exist, but they're different. So let's move on to f here. The limit as x approaches 7 from the left. So I find 7, and I'm going to approach from the left. Now it appears that the graph is going down here. It looks like a vertical asymptote. And when that happens, we say the graph is approaching negative infinity. Okay, and I'm sorry, the limit is approaching negative infinity. And we have a vertical asymptote of x equals 7. If I approach if x approaches 7 from the right, so I'm coming over on this side, I can see that now the graph goes up in this direction. So again, same vertical asymptote, but the graph is going up, okay, and my outputs are approaching infinity. Okay. Finally, my limit as x approaches 7 of f of x, again, does not exist. Okay. So one last thing I want to say is that infinite limits correspond to vertical asymptotes. So if you attempt to compute a limit and then you get positive or negative infinity as your limit, then you know you have a vertical asymptotes. So this is our calculus definition of vertical asymptotes. I want to mention one other thing, and that's functions that are similar to this function. Here I have 1 over x, and I want to think about the limit as x approaches 0 of sine of 1 over x. Okay, as x approaches 0, let's say from the right, I know that 1 over x is going to blow up to infinity. Okay, so as we get close to 0, this grows it keeps growing, right? It gets arbitrarily large. So now if I take sine, the sine function is going to continue to oscillate. It's going to begin to oscillate wildly near 0 because 1 over x is, it's blowing up. So we're going to have some behavior like this in our graph. The graph does something like this, and then it begins to oscillate wildly near. I couldn't even draw it, right? It's oscillating wildly near the origin. So in this case, we would also say the limit does not exist. Now the next thing I want to do is I want to look at another limit. This is a rational function, and we're going to try to determine this limit in 3 different ways. The very first thing I always do when I'm trying to compute a limit is I just try to evaluate the function. I say, oh, let's just see what f of 1 is. It's 1 minus 1 over 1 squared minus 1. This is undefined. So I instantly know that the 1 is not in the domain of my function. That does not mean the limit doesn't exist. That just means that my function isn't defined there. That's all. And this is what we called an indeterminate form. So we just leave a question as to what is the limit. Well, indeterminate form is like no info. So we move on. Okay, the first technique I'm going to use to try to evaluate this limit is I'm going to try to use a table of values. Now I'm trying to evaluate the limit as x approaches 1. So I'm going to start off by approaching from the right. I'm going to choose values of x that are to the right of 1. So we have 1.5, 1.1, 1.01, 1.001. And I'm getting closer and closer to 1, but I'm approaching from the right. When I plug these values into my calculator, I get 0.4, 0.476, ... etc. And you can sort of see the pattern here that it appears that as I get closer to 1, f of x is getting closer to 0.5 or 1/2. So according to the table, it looks like the limit as x approaches 1 from the right of my function is equal to 1/2, 0.5 or 1/2. I'm also going to approach 1 from the left. Okay, so I choose values that are smaller than 1. I plug in 0.5, and this is my output. I plug in 0.9, this is my output, etc. And it's very clear that as I get closer to 1 on the left, that my output is getting closer to 0.5. So it looks like the limit from the left is also 0.5. And so it appears, I can't say with 100% certainty, but it appears that since the left and the right limit are both 0.5 and they're equal, that the limit as x approaches 1 of my function is equal to 0.5 or 1/2. Now that's just what appears to be happening. Okay, so that's what appears to be happening, is that my limit as x approaches 1 is 1/2. But it's possible that I chose values of x that, look like this was happening, but that this might not actually be what's happening. So when you read through the textbook, you'll see an example where I get behavior similar to this, but this does not give me the correct limit. So please take a look at that example. So the second method I can use is I can graph the function. So if I graph the function f of x, then indeed, I can see that the limit as x approaches 1 is indeed 1/2. Okay, so this function is essentially, in order to graph this function, I'm just going to graph the function 1 over x plus 1. Okay, so in this case, the way that I graph the function is that if I factor this, I realize that I can cancel these two factors, and that as long as x is not equal to 1, this is equal to this. So I can call this my new function g of x. And the only difference between the graph of f of x and g of x is that g of x would not have a hole here. So this suggests another way that I can evaluate this limit. The idea is that f is equal to g except at x equal 1. So algebraically, we can compute this limit by saying that the limit of, as x approaches 1, of x minus 1 is equal to the limit as x approaches 1 of g of x, the other function, The limits are the same, even though the functions are not. This function doesn't have any strange behavior, so when I plug 1 into this function, I get 1 over 1 plus 1, which is 1/2. Okay, so this is another way to evaluate limits. So at this point, we have 3 techniques. We can evaluate limits using the graph, we can use a table, or we can use algebra and find a function that has the same limit as our function. So the key thing to remember here is limits don't care what happens at this number. Okay, limits only care what happens, what the function is doing around that number. So it's about nearby or local behavior. We don't care what happens at x equal 1. We care what happens near x equal 1. I also want to do an example involving an infinite limit. Computed algebraically. The first thing I always do when I'm trying to compute a limit algebraically is that I try to substitute this number into my function. In this case, 5 plus 7 gives me 12, and 5 minus 5 gives me 0. This immediately tells me that my function is not defined, so f of 5 is undefined. So f5 is not in the domain. Okay. I also take note of the fact that the denominator is equal to 0 when x is equal to 5. But as I'm approaching 5 from the left, so let's say these are my x values, I'm approaching 5 from the left. So for instance, I might substitute 4.9, that's a nearby value, 4.9. I notice that the denominator is not only tiny, but it's negative. So when we take a positive number and we divide it by a tiny negative number, the result is a huge negative number. And so in this case, we can see that the limit is negative infinity. Now, you can verify this by graphing the function. If I were to graph this function, it's a rational function. The graph would look something like this. And you can see that as we approach 5 from the left, the graph heads down in this direction. We have a vertical asymptote, and the limit is negative infinity. That's what we captured here. So just to recap, the idea is that whenever you try to compute a limit by plugging in, this value into your function, if you obtain a positive number in the numerator, and in the denominator you obtain 0, the next thing you want to do is to determine if these tiny, tiny, tiny numbers are going to be negative or positive as you approach 5 from the left in this case. And then that quotient will will give you some sense of whether you are approaching negative infinity or positive infinity. Here's another example of an infinite limit. So here I'm approaching 0 from the right. My x values are approaching 0 from the right. So these are positive numbers. My function here is a natural log function. So what is this limit equal to? The best way to understand this limit is to remember the graph of the natural log function. And it looks something like this. So we have a vertical asymptote at x equals 0, and my limit is negative infinity. Okay, one more example. This isn't an infinite limit, but it is a very important limit that will come up later. And so let's do the limit as x approaches 0. I'm not going to do right or left. Of sine x over x. Okay, so if I substitute 0, I get 0 over 0. So that's indeterminate. It's no info. The function is simply undefined at 0. So in this case, I'm going to graph the function. And if I graph the function, I find that, well, there's the hole in the graph. The graph does something like this. So the limit of this function is actually 1. And I determined that from graphing it. But you could also, there's a more rigorous proof in your textbook, so please take a